Let's think about comparing the two models we did for the school district test score data. The first model we did, we didn't have any other information about the school district. We didn't have any demographics or anything. So we were just predicting these numbers by using the average. And we could say that's equivalent to kind of using a horizontal straight line. Here it's against the row number in the data set, but it could be against any x variable. If our prediction is always the same, we're just going to get a horizontal line. And we were getting a root mean squared error there for that prediction of about 85. And then when we decided to use some x variables to make predictions, we were using coefficients and an intercept. And we had a formula here that multiplied those coefficients by the values for each school district, added the intercept, and then we took the residuals, and we had this root mean squared error. And 61 as a root mean squared error is less than 85 as a root mean squared error. And we could ask how much better is it? So here I'm just copying the root mean squared error from the other sheet. And a nice way to think about that is to basically say what's the new size of the residuals. This is basically the standard deviation of the residuals divided by the standard deviation of the residuals, where we were just predicting the average for everything. So a very, very simple model. And for technical reasons, it's nice to take that ratio of the root mean squared error for our new residuals divided by that very simple model's residuals root mean squared error, square that and subtract it from 1, and that gives us this value here. So we could say that our residuals are now 47% smaller than they were, are now 47% smaller than they were with the simpler model. The squaring, the fact that we're squaring isn't all that important there, it's just for technical reasons. But this 47% is interesting because if we did a regression, a multiple regression using the same x variables, we can see that that's actually equal to our r squared. So r squared is defined as what we just did, basically 1 minus the root mean square for our regression residuals divided by the root mean square for just predicting the average y value for everything, squaring that, subtracting from 1. That's also called the coefficient of determination, r squared, and it's saying what proportion of the variation, actually the variance or the squared standard deviation in the y variable is predictable from the x variables. So if you look farther down here, this is the formula you'll often see. SS here means sum of squared, so sum of squared residuals over sum of squared total based on just the average. If you take the mean, you're just going to be dividing by n in the top and the bottom. So some people like writing sum, some people like writing mean. And we were taking the root and then squaring it. You could just leave it as the squares. So that's the definition of r squared, and that r squared is also called the coefficient of determination. And we computed it using our two explicit models and also had the regression tool do it. This also helps explain why r squared is always between 0 and 1, because if our new model is no better than the old one, then the residuals have the same size as the old. This fraction is something over the same thing, which is 1. Subtract from 1, you get 0. So an r squared of 0 means your new model is no better than the simpler model. If somehow you got all the residuals to be 0, then their sum of squares would be 0, and you would get 1 minus 0, so you get an r squared of 1, which is that you have perfectly predicted the y values from the x values, which is pretty rare.